by Zhi Li, who will tell us about how much entanglement is needed for quantum error correction. So please.
Okay, thank you so much for that introduction. Yeah, today we'll be talking about entanglement and quantum error correction. This talk is based on these two papers listed here in collaboration with Sergey, Bravyi, Dongjin Li, and Beni Yoshida. Okay, so a bit of motivation. In recent years, we have witnessed so many very wonderful progresses in quantum error correction. But in this talk, I want to maybe take a step back and ask more basic but more conceptual question, which is, why does quantum error correction work? Why is it even possible? And more precisely, I want to ask, why do quantum error correction code exist? Well, of course, we know it exists, but in this talk, I want to emphasize this more conceptual aspects, which is that entanglement is very crucial for quantum error correction. So entanglement, well, I believe everyone here knows entanglement, but since there are so many different aspects of entanglement, so let's still look at this very basic example of Bell pairs. So here we have two different states. They are different because the sign in the middle are different. But if you compute the reduced density metric of both sides, you get the same answer. In this case, it is just the maximally mixed state. So from this example, you can see that, okay, entanglement, first of all, it is not the product state. But more importantly, for this talk, it means that even if you know all the local information about all the subsystems, here it is the low A and low B, you still do not know the full information of the whole system. And this is a feature of a defining feature of entanglement. And this phenomenon happens in a very extreme way in quantum error correcting code. To see that, let's think about one of the equivalent conditions of quantum error correction code, which is called local indiscriminability, or the Kneel-Laflamme condition. This condition says that code states must be locally indistinguishable within code distance d. In other words, if you pick two different states, phi and phi prime, but you compute the reduced state within a subsystem A, for which you assume A is smaller than the code distance d, then you will get the same answer, even if you start from the two different states. So from this condition, we can see that in the QEC, there is an extreme version of entanglement in the sense that local system really knows nothing about the global system. So in the QEC, quantum information is encoded in a very non-local way. It is encoded by the pattern of entanglement. So we can say that entanglement is really crucial, really necessary for QEC. And we can make this statement, make this observation more precise. So let me remind you this simple fact. We can show that all code states must be entangled. In other words, there does not exist product states in the code space as long as your code distance is bigger than 1. And the proof is very simple. It's almost a one-line proof. So you assume by contradiction there exists a product state, let's say product state of 0 in this code space. And then let's pick another code state, let's call it psi. And now we plug in those two states into the Kneel-Laflamme condition, and we get one equation for each qubit. And so we solve this system of equations. We can see that the only solution for this state psi will be that this state is equal to the product of 0 state. And this means that the code space is actually one-dimensional, and it cannot encode any quantum information, which is a contradiction. Okay, and beyond this simple observation, we can actually say something stronger. And also, let me remind you another fact, which is that code states are not only entangled, but they must be long-range entangled in some sense. More precisely, I mean, any circuit that prepares any code state must be at least have depth log d. And the proof is also very simple. It's also almost a one-line proof. So let's assume we'll have a code space, which is a NKD code. And here, the k does not need to be an integer because we are talking about a very general code. And now let's apply a local unitary circuit with depth 1 on this code space. Now, because of the Kneel-Laflamme condition and by looking at the light cone of the circuit, you can immediately see that after you apply this circuit, you get the new space, which is also a code space. It's a code space for the same n and same k, but maybe a slightly smaller code distance. But very importantly, this new code distance must be at least d over 2. And because of the observation from the previous slides, if you want to get the product state, you have to decrease the code distance all the way down to 1, which means that you have to apply at least a circuit of circuit depth larger than log d. Okay, up to this point, I hope I have convinced you that long-range entanglement is really needed for quantum error correction. And in this talk, our goal is to make this observation more precise, more quantitative. We want to ask more precisely how much long-range entanglement is needed for quantum error correction. And in other words, we want to ask how far quantum error correction codes from short-range entangled states. To solve this problem, first of all, we have to define what we mean by how far and how much. And so in this talk, I will be using a many-body entanglement measure that has a geometric feature. It is called geometric entanglement measure. So let's say we have a quantum state psi, and we have a set of unentangled states, which is the set of the product states, and we want to quantify the amount of non-productness, the amount of entanglement in this quantum state psi. In quantum info, if you want to compare just compare two states, then it's very simple. We just compute the fidelity, which is just the inner product of two pure states. And here now we have one state and one set. Then mathematically, it's very standard to define the distance as like the distance will be defined as a minimal distance between this given point and all possible points in this set. So in other words, we are going to maximize the fidelity, maximize the overlap between this given co-state psi and any product states. And so I will be writing this maximization value as in an exponential form, and the thing in the exponent will be called geometrical entanglement measure, or a GEM. So in one of the previous slides, we have shown that there does not exist any product state in the code space. So in other words, we have already shown that the left-hand side which must be strictly smaller than 1. So in other words, in the language of geometric entanglement measure, it is just to say that the GM for any code state must be strictly positive. But there is a problem of this geometric entanglement measure, which is this GM can be very easily spoofed. So to see that, let's look at this very simple example, which is a state that is just a branch of Bell pairs. To prepare this state out of the product state, we can just apply some like C0 gate parallelly. So we can prepare this state by just a unitary circuit of depth 1. But if you want to compute this the GM for this state, you will see that the GM is actually linear in this case. And so this is not good because we are trying to find something to quantify the long-range entanglement in some quantum states. But here, this state has only short-range entanglement, but still it has a very large GEM. But solving this problem is also very easy. Well, previously we defined the GEM by maximizing the overlap between this given state and our product state. And now, to capture all the short-range entangled state, we just replace this set by a larger set, which is the set of short-range entangled state, or states that can be prepared by a low-depth circuit. And we still do this maximization, and we will still write this maximal value as an exponential form. And now this thing in the exponent will be called a depth t GM. And it is obvious that this depth t GM will be decreasing as a function of circuit depth t. So our goal of this talk will be trying to derive some lower bound for this GMT. And if we can do that, then we'll have a bonus, which is that we can prove circuit lower bound for circuit to prepare a code state. This is because if you want to prepare a code state up to some epsilon error, then you just plug this epsilon into the formula, and you solve this inequality. You get a lower bound for this circuit depth t. Okay, so now we can make this talk more precise. We want to ask, is geometric entanglement measure nicely lower bounded as a parameter or as a function of the code parameter nkd? And maybe the first order question is whether this this measure is always bounded away from 0, besides being positive, but whether it's always bounded away. And also, intuitively, because we have argued that this long-range entanglement is needed for quantum error correction, so we might guess that the more protection we want, the more entanglement we need. So maybe we'll also conjecture that this GM will always be lower bounded as a function of D, because D is a quantity that quantifies the quality of protection. But maybe a bit surprisingly, we have a current example to show that the GM can actually vanish. So here is an example. We consider 2 quantum states. The first state is a superposition of all 0 and all 1. The second state is a superposition of all base strings with a Hamming weight 2. In other words, it's a decay state with Hamming weight 2. And if we plug those 2 states into the Cornell-Lapham condition and do some calculation, we can see that if we choose P equals 2 over n, then those 2 states will satisfy the Cornell-Lapham condition exactly, meaning that those 2 states will span a code space with D equals 2, K equals 1. But if you look at the first state, it has actually a pretty large overlap with the product state, all 0. Here, the overlap is 1 over P, so according to our definition, the geometric entanglement measure is actually of order 1 over n. And based on this example, we can actually do something more. So we can, using a code concatenation, to construct a family of state so that we have a fixed D, fixed K. But if you tune the number of qubits, then you will also have a vanishing geometric entanglement measure. So this example shows that in general we do not expect any nice lower bound for the GM. It may even vanish as n goes to infinity. But on the other hand, which is the main message of this talk, is that under some conditions, we do have many lower bounds for the GM. And these conditions include constant rate condition, stabilizer condition, LDPC condition, and even stronger constant rate LDPC, and also a topological condition. So as long as the code satisfies any one of these conditions, we will get some lower bound that I will show. But unfortunately, the proof is very different in different cases. So I will not be able to show all of them, but maybe let's see, maybe I can show 2 of them. Okay. So the first result is about the GM for any quantum error correction code. We have the following result, which is the overlap between any product state and any code state in any quantum error correction code will always be upper bounded by this guy. And here, this H is the entropy function. So just from this form, you can see that you can guess that the proof is some sort of entropic proof. And as a corollary, if we assume that this code has a constant rate, meaning that K over D is some order 1 value, then this H inverse of K over N will be also a constant value, so that the right-hand side will be exponentially small in D. In other words, we show that for constant rate quantum error correction code, the GM must be linear in D. And this is the first result. And second result is that we show that for any stabilizer code, this GM must be at least D minus 1. And this inequality actually be saturated just by the source code. And this statement is, can be proved in the relatively easy way, so I will sketch a proof. So let's assume we consider the overlap between a code state and all 0 state, for instance. And so we are going to upper bound the overlap between this code state and all 0 state. And the first step is simply to use the monotonicity of fidelity, and so we can upper bound this guy by looking at the overlap between the code state and the product state just on the subregion R. And the second step is using a technical lemma. This lemma, we found that for any stabilizer state with code distance D, there always exists a subsystem R for which the size of R is D minus 1. And if you reduce the state to the subsystem, you will get a maximum mixed state. If you plug in this maximum mixed state into the formula, you can see that you immediately get this 1 over 2 to the minus d. And to prove this lemma, you just use induction on the codistance, and to use another observation about how the codistance change after you do the measurement on the codes. Okay, the next result is about the LDPC code. So in our definition, LDPC also stands for low density parity check, but we do not assume it is a stepladder code. In other words, the checks does not need to be poly. So we can assume we just need to assume it's the commuting projectors. So a very typical example for non-poly checks is this third figure, which is called the string-line model or the level model. It is a model for non-abelian topological quantum computation. Okay, so here is the result for LDPC code. We show that for any codistance, for any code in the LDPC code with codistance d, its product with any product, its overlap with any product state will always be lower bounded, upper bounded by something which is exponentially small in the codistance. And if we combine this LDPC condition and the constant rate condition, we can even see something stronger. We can see that in the constant rate LDPC case, this overlap is actually upper bounded by something exponentially small in n, not in d. So in the second case, the GM is actually linear in n. And this stronger example can be applied to, for example, the hyperbolic surface code. Okay, and our last result is about topological codes. So before showing the general result for all the topological codes, let's take a look at our favorite toric code. So for toric code, we have the following result, which shows that the geometric internal measure for any code state in the toric code subspace will always be lower bounded by n over t squared, where t is the circuit depth. And in particular, if you choose t equals 0, you will get a product overlap, which is upper bounded by e to the n. And also note that the toric code is also a LDPC code, and it's also a stepladder code. But if you use the previous results for the toric code case, you will only get e to the minus square root of n, because for toric code, the codistance is square root of n. But here, we are using some extra structure of the toric code. So the extra structure we use is the emergent anyons in the toric code. It is well known that for toric code, you have like the vacuum sector, the E sector, M sector, and the fermion sector. And if you braid the M anion around the E anion, you'll get the -1 phase. So very crucially, we show that in any system, every time you have this non-trivial braiding, you can get the uniform lower bound for this GEM. And we can also show that this GEM, in this case, is actually some sort of additive, so that you can divide the system into several different patches. And for each patch, you just run this sort of braiding experiment, and you got a GEM lower bound for each one, and you can sum of them together, so that you get a GEM which is lower bounded by something is linear in n. And so as a toric code, we can show the result for a general stepladder code. We show that for any 2D stepladder code, this GM is always lower bounded by d squared over t squared. And here d is the codistance, and t is, again, the circuit depth. And the proof idea is also pretty similar. So we use a technical talk called clean lemma, and we show that for any 2D stepladder codes, there always exists some sort of emergent anyons for which you can do this non-trivial braiding. And then we can do this braiding for different patches, and add them together, we get this lower bound of t squared over t squared. Okay, and that's everything for this talk. So let's just recap. The main result is that first, we show a counterexample for which the GM is not necessarily lower bounded, in the sense that it may even vanish as n goes to infinity, even if you have a non-zero DNK. And on the other hand, we show that the GM is indeed lower bounded for these 5 different cases. In the first three cases, we show that the GEM is lower bounded by something linear in D. And in the last two cases, we show that it's actually linear in N. And that's everything. Thanks a lot. Thank you.
All right, we have time for many questions, actually, but.
Hi, thanks for the great talk. I'm just wondering, in your definition of GAM, you've been always considering the overlap between your code states and product states, or like via some finite depth unitary. So I'm wondering, but what we usually mean by entanglement is separable states. So can you comment on like what would happen if you replace this product state here by like maximization of all possible separable states?
Oh, first of all, I'm talking about pure state. So I think for pure state, it makes sense to think about just like short-range tangle state. But on the other hand, you can also think about the problem for mixed state. For mixed state, we do also have some results. Like we can, for example, we can upper bound the fidelity between, say, some state which have some code feature and all those so-called short-range entangled, like short-range entangled mixed state, which is more general than a separable state.
Well, I mean, but suppose if you replace this product state by a separable state, would you expect like your results about GM to change a lot, or are they basically the same scaling?
You mean for pure state?
Okay, we can just talk about pure state for now.
I mean, yeah, I mean, it's I think it's a convex combination for pure state. So you can just think about pure state.
All right.
Hi, thanks for the nice talk. I'm wondering whether this notion of GEM has anything to say with the fault tolerance of the error correction codes, like especially like under decoherence, for example, like where it provides some bounds of fault tolerance directly.
Oh, that's a good question. Actually, I don't know the answer.
Thanks for the talk. So I think in the case of many-body physics, people say that long-range entanglement typically can infer some lower bound on the circuit depth, try to prepare such states.
Right.
I wonder in your case, maybe that's already your talk, but in your case, can you get just some lower bound to prepare some?
Oh, yeah. So maybe I should be more clear. Yeah. So in this slide, because you can see that if we already have some lower bound as a function of t, now you want to prepare this state, you just plug into your tolerance of the error into this formula and solve this inequality. You get lower bound for circuit depth.
I see. Thank you.
Hi, thanks for the nice talk. So I'm wondering if there's a straightforward connection between von Neumann entropy and GEM. Is there some way that I can bound von Neumann entropy and vice versa, or some using some?
Oh, you mean like a von Neumann entropy of a bipartite, like a bipartite cut?
Yeah, let's say I consider some set of von Neumann entropy for different subregions, and I construct a function of that, right? Is there some way where I can relate that to GEM?
Yeah, I think if you have a lower bound for GEM, you can get a lower bound for like von Neumann entropy for any cut. Well, simply because it's you already know it's far from a product state or.
Yeah, I guess my question is more like, what is GEM measuring in terms of von Neumann entropy? Is it like measuring some sort of average sense of how entangled different subregions are, or like, whether there's such a physically intuitive picture for that?
Oh, I see. Yeah, so I think maybe a good picture is to think about at least in this case, it does measure some kind of entanglement, like average sense entanglement everywhere. Yeah.
Thanks.
What are your thoughts on modifying the definition of the GEM to rule out the counterexample?
Sorry, modify it to?
Modify the definition of the GEM to rule out the counterexample? You must have tried that.
Sorry, can I?
So you have the definition of the GEM, and then you say, oh, this counterexample, it doesn't really work. What are your thoughts on changing
this example?
Yeah, exactly.
Okay.
Oh, no, not that one. This one, the one with the P. very close to product state, 1 minus square root 1 minus p.
Oh, the concatenate code.
Yeah.
Yeah.
So you
This
must
one?
have tried to change the definition of the GEM to rule out this example.
Oh, actually, I didn't try.
Oh, you didn't try? Okay.
Yeah.
Thank you.
Thank you.
Thanks for the nice talk. I have a question about the GEMT. You defined it to rule out the case of the all short distance entanglement. So do you have any results with respect to this GEMT? I think.
Oh yeah, sorry, I forgot to mention. Yeah, because of this observation that if you apply a unitary circuit for a code, you can at most reduce the you reduce the code distance by a factor of 2 to the t. So at least in the first 3 results, you can simply replace d by d over 2 to the t. So you get a program for GMT, not GM0.
Okay, thank you.
Thank you.
Yeah, thanks for the nice talk. I have a question about this product case. I mean, for the product state, you can actually parameterize the product state, and given a error correction code, can you efficiently compute this GM?
Oh, yeah. Actually, for this thing we tried. Yeah, I don't think you can efficiently compute this GM because it's just optimization over so many different parameters. And actually, even for simply the 5QV code, we actually tried the 5QV code. For that thing, the maximum value is not obtained at any really nice looking point. It will be obtained at a really weird angle. I have no idea about what it is.
Okay. Yeah. Thank you.
All right. If there are no more questions, let's thank both of our speakers again.